Hello everyone, welcome back to another video with Mr. Coder, and in today's video I'm going to show you how to solve Wolf. Question E from Codeforces Round 1020, Division 3. So Wolf has found n sheep with a tastiness value of P1 through Pn, where P is a permutation. And in this case, permutation is an array that contains every integer from 1 to n exactly once, inclusive. So Wolf wants to perform binary search on P to find the sheep with tastiness of K. But however, P may not necessarily be sorted. And as you should know from binary search really only works if an array is sorted. The success of binary search on the array L of R for K is represented as F of L R K, which is defined as follows. So if L is greater than R, then F of L R K fails. Otherwise, let M is equal to L plus R over 2, rounded down. And then if P of M is equal to K, then F of L R K is successful. If P of M is less than K, then F of L R K is equal to F of M plus 1 R and K. Otherwise, if P of M is greater than K, F of L R K is equal to F of L M minus 1 and K. So it's just standard binary search, basically. So if you don't code binary search like this, it's not that hard to change into it. It's very similar to most types. It's at least the same as I learned it, of always updating the right to mid minus 1 and left to mid plus 1. So if you don't know how that binary search works, I do have that binary search in my code, as I'll show later. So then Cal the Nerd decides to help Wolf out, and he's giving Q queries, each consisting of 3 integers L, R, and X. Before the search begins, he may choose a non-negative integer D, and D indices I of 1, I of 2, all the way to I of D from 1 to n, where P I of j is not equal to X for all j. So that's basically saying you cannot move around the value that of the sheep with tastiness K. So then he may reorder any the elements P of I through 1 through P of I of D, however he likes. So for each query, output the minimum integer D that Cal the Nerd must choose so that F of L R X can be successful, or report that that's going to be impossible. Note that the queries are independent and the reordering is not actually performed. So in this case, the first example, second query, so 1, 3, and 4. So you can notice that since 4 does not exist, it is impossible. But 1, 5, 4, isn't the best example to look at, but it's always going to work since this binary search is sorted. But if we go to the next example, then we get to 3, 4, and 2. So 1, 2, 3, 4. So it's 5 and 2, and you're searching for 2. But then you're gonna search for you're gonna search for the numbers, and then you get 5 first since it's rounded down, and then you're like, oh, 5 2 is less than 5, so it's got to be less. It's got to be under it. So then if you go under, there's no more room for indexes, so it's unsuccessful. So that's why you need to consider moving some. But notice that if you only can reorder 1, it's going to do nothing. So you have to reorder 2 of the numbers so that it would be 2, 5 instead of 5, 2. Which then that shows that the answer is 2. That's basically the gist of this problem. So, and notice the time complexity you have to achieve. So for each, there's 2 times 10 to the 5th queries, which means obviously you can't loop through the array. So that hints at a log of n solution. And that's a good assumption when you see that this whole problem is about binary search, which is a log of n algorithm. So then, and what I did in my code here, sorry for my long template, that's just a template I did for fun, actually. And yeah, a lot of it's useless. So you don't need to bother looking through it since I barely use any of it. Except I do have an input function, but that's like off topic. So basically for this problem, I mapped the sheep indexes, or the sheep tastings value to its index. So then when I get K, I can actually use it with the proper array index. I loop through the Q queries and then I make it zero index. That's a general thing that I do. And I know a lot of people do it as well to make everything zero index. So you can just define an array of that exact length. And then this is why I define the map for the index. So the first thing to notice is if it's not in the range of A, B, then it's never gonna, no matter how you reorder the elements, even if you could reorder all K, it's still never gonna be in there. So then it's when you do binary search. So then in this binary search, you check if the mid is less than the index, because that's just going to be standard binary search, basically. But you're searching for this index instead. So, and then you need to use vec of mid, which is just the value of the current mid to see what you need to update. So you need to check the number that is less and the number that you can change for more. So f more and u less, basically those are different variables that can use. So u less, you need to, it basically says which ones you can replace it with. So that's why each of these are defined differently. And that's the most confusing part of this problem. You need like so many different variables in your binary search. So if mid is greater than index, then you just go with then it's basically the opposite. So then you need to check if, and these if statements basically say that if it won't go there in the function currently, then you'll need to move one. So that's what less and more are for. Then these are for changing, like which ones, how will it help changes in the future? So then if it's equal to the index, then you break, since then it ends up getting there. Notice that this is how you do the binary search in this case. You have while L is less than or equal to R, that's a difference from normal binary search. And you do L plus R's over 2, and this defaults to rounding down. And notice how I define L equals mid plus 1 here and R equals mid minus 1 here. It won't be, because you do plus 1 and minus 1, it won't be infinite loop, and since it's less than or equal to, you won't miss a single element. So that's how I always code binary search. I don't know how you code it. And if you have any questions about it, you could, of course, just comment down below. But then afterward, you check if the just because an element is inside the range does not mean that it's always possible. Like, what if there aren't enough elements to rearrange, since you can't rearrange the K itself, so you have to rearrange all the others. So that's what this is for. You need to check if the number of ones you have to make to go less are greater than x minus 1, which is the number that are actually less. So that's basically just the condition to check to see if it's impossible at this point. And then you just calculate the total, which is the number of more plus the number of less. Those are the ones that you obviously need to change, otherwise it won't go there. And then these are just to determine the how many, because f more is and f less is how many you can use that can change it. So like f of more is basically saying how many how many mores can you move to this more as a swap as reshuffling the array. So that's why I need to add this. And notice that it's not just simple like more plus less, as you might think originally, since you also need to consider what if you move it, what if you can't reorder the current elements? You have to add more. And that's why you have to have this if statement in the first place. So then you just print it out. And then you do this in query. So this problem, it isn't any pre-calculation besides this map, which is barely anything. It's mainly all inside of each query loop. And the key thing to notice is that you have to solve each query in log n time. So that really hints at just doing binary search, like it says in the problem here. And you have to follow it step by step. Otherwise, you'll get maybe like off by 1 or whatever if you don't follow this exact same binary search. But yeah, if you know that and you know binary search, then this problem is doable, and you really just need to keep doing calculations on paper to determine, like, you just need to be a robot and like the code. Like you have to act like you're running the code and see like at this point, what should the number be with your human brain, and what will the code need to do to get there? So these types of problems really aren't just like, oh, you see the solution, you do it. You have to think about it and use your pen and paper. So that's always important to have. So if you don't use that, you definitely should. So yeah, thank you for watching this video. If you like this video, please like and subscribe, and I'll see you in the next one. Bye.